Hi, everybody. My name is Richard. First, I just want to thank everybody. This has been a really fun conference. It's been really great meeting everybody and exchanging ideas. I have a poster outside that is dealing with, I think, one of the biggest problems in data analysis for astronomy looking forward, that being crowded field photometry. This is a problem because as our telescopes get more sensitive and our ground-based telescopes get more sensitive, we're picking up the light from a lot of fainter sources, but we don't have the angular resolution to resolve them. So what ends up happening is these cases of extreme blending. And this is guaranteed to become more exacerbated as we go forward. From a modeling perspective, this is a challenging problem because normally if you use something like a Markov chain Monte Carlo method, ideally you want to sample the space of all catalogs that are consistent with an image. But let's say I look at one blob of light, and I don't know whether it's one source or two sources. Being able to explore that catalog space is difficult because I'm changing the dimensionality of my model. So we're using a method called PCAT, which is a Bayesian hierarchical model that implements transdimensional sampling. And so what that means is that we can sample within a model that has a fixed number of parameters, but we can also construct proposals that go from one model to a different model that has a different number of sources. So this might be of interest if you're trying to see whether sample between the possibilities of one source being like just one blob being one source, or being two sources, or maybe a galaxy and a star, or any sort of combination. And so it turns out that when you do this, you can probe a lot deeper into the field that you're looking at and disentangle a lot of highly covariant sources in a way that's going to be relatively efficient. And so there's been work that's been done to apply this to the single band case, and we find that compared to something like DAO-FOT, if we compared to like a reference Hubble catalog, we're going over a magnitude deeper in completeness, and we have a lower false discovery rate up to some magnitude. We're looking at the SCSS field from Stripe 82 of Messier 2. So this is actually a field that SCSS, its photometric pipeline, timed out on because it was too crowded. But my project has been looking at how multiband information can enhance source detection and improve these problems of deblending. So, one of the immediate advantages you get with this is the improved signal to noise from, jointly fitting observations. But you can also start to use color priors that can enhance your detection. And, this is a delicate balance because you don't want to impose color priors that are too strong, to such that you're disfavoring sources that might be unique in color space, but they can help constrain the overall parameter space that you're exploring. So we find that we're able to use multiband information to directly disentangle blended sources and also improve the completeness in two-band fits by another 0.4 magnitude. So, compared to DAO-FOT, this is nearly 1.5 magnitudes deeper using the same data. There are plenty of other applications. I'm interested in hearing your thoughts on different circumstances where maybe you might use more constraining spectral information, or you might have other sorts of challenges. But feel free to ask any questions outside. So, thanks.